My name is Kwanyong. I'm currently in the School of Energy and Chemical Engineering of UNIST, Korea. First of all, I'm really honored to have a chance to give my research topic today here. I'm really thanks to the committee members for this good occasion. So today I'm going to talk about the flexible crystalline silicon photovoltaics, mainly about the light management between the silicon and instant sunlight. So with surface structures, mainly one-dimensional microwire structures. So before starting the main contents of today's talk, I think I need to briefly explain about the solar cell because many chemists are listening to this talk. So as all of you know that the solar cell is a very simple energy conversion device from the light energy into the electrical energy. So many researchers are mainly working on to improve the efficiency as much as you can see in this slide. A solar cell needs a space. So in urban area where we use the most of the energy, there is no enough space to install this kind of solar panel. So we have to find out another strategy to use this solar cell. One of the possible candidate is the flexible solar cell. So if we realize the flexible solar cell, we can easily spread out our solar cell technology into our daily life. And if we realize the flexible solar cell, we can integrate this technology into the building as a building integrated photovoltaics or the vehicle surface, even on the mobile devices. So I think that we have to consider three different important categories for the flexible solar cell. The efficiency is the most important, the key parameters, and also that the stability is also important. And flexibility, of course, is very important. So among them, the stability is very key, the parameters regarding the realization of the flexible solar cell, because currently many researchers working on this flexible solar cell using emerging materials such as the organic dye and organic polymer materials or perovskite. In this case, although they are trying to develop this device very well, and then efficiency reached meaningful value over over 10% or around the 10% at this moment, but still they shows the very poor stability due to that the chemical instability of the active materials. So although this emerging material-based flexible solar cell research is very important, but we need to think another the research aspect for this flexible solar cell development. So we can also consider crystalline silicon as an active material. As you know, that is crystalline silicon so far show that highest efficiency of 26.7% and the 95% of the industry and is covered by the crystalline silicon. However, the crystalline silicon materials intrinsically has the critical problem because it is the crystalline nature, so it can easily broken like this image. So how to solve this the problem, this rigid crystallinity of the crystalline silicon is the key point when we realize the flexible solar cell using this crystalline silicon materials. But fortunately, people already know that the crystalline silicon can be flexible. If we decrease the thickness of the crystalline silicon, for example, less than 50 micron, in this video shows that the 50 micron thickness crystalline silicon wafer, it can be flexible, very meaningfully flexible. So if we increase from the 50 to 80 micron, the crystalline silicon substrate is linearly the bending radius increased. A bending radius is the key terminology we use for the for testing the flexible property of the materials. The smaller bending radius indicate the better flexibility. So we know that is if we decrease the crystalline silicon vapor, we can have better flexibility, but still there are problems. There are two critical problems when we decrease the substrate thickness of the crystalline silicon. First thing is that if we decrease the silicon thickness from the general thickness of the wafer 200 micron to the with a flex of 50 micron, we can have the nice flexible property of the silicon substrate, but due to the indirect band gap property of the silicon itself, the near IR absorption getting poorer and poorer. So, sorry. And more that there are surface reflection is also a very critical issue. Flat silicon surface, they reflect about the 30 to 40% instant light. So we have to have the surface structure on the silicon surface to minimize the surface reflection. So industry, we generally use this kind of pyramidal structures to minimize the surface reflection. Only applied simply with the pyramidal structures, we can significantly reduce the surface reflectance, as you can see in the left bottom figures. However, in case of this pyramidal structure, there are many crack initiation sites between the pyramidal structures. This crack initiation site could be a problem when we do the bending. So starting from this crack initiation site, a silicon substrate itself can be broken by through the bending process. So when we measure the bending radius, with pyramidal structure on the planar silicon substrate, shows that the almost twice value of the bending radius. This means that even with the pyramidal structure, we can minimize the surface reflection significantly, but bending flexible property is getting poorer. So we have to find another candidate for the surface reflection minimization in this application. So I think the best solution is one-dimensional wire surface structure, because wire surface structure shows a high light absorption capability and also very stable flexibility, as I explained a little bit later. And also, instead of the vertical PN junction, radial junction can be applied in this one-dimensional wire structures. But question is that which dimension is the best candidate for the better flexible solar cell application, nano wire regime or the micro wire regime? As you all know that nano wire is the really, really nice materials, nice geometry for many different applications, because it shows the almost perfect light absorption property. However, it is not easy to form a radial junction using this kind of one-dimensional structure, because in general, conventional doping process, we have the over 100 nanometer depletion region. So that means less than 200 nanometer wire diameter can be fully depleted. That means it cannot be used as a conventional PN junction. And also that as we increase the surface area of the nanowire array structures, high surface recombination is also a very important issue. However, microwires, although they show less effective light absorption property, but still is good. They show still good the performance as a anti-reflective surface materials. And also that it is easy to form radial junction by diffusion-based doping process. So as a conclusion is almost 1 or 2 micron diameter wire range would be the best geometry of the one-dimensional wire-based solar cell application. And also, this micro-wire structure is very, very important regarding the surface flexibility and mechanical stress issue. Starting from the 50 micron crystalline silicon substrate, if we increase the bottom substrate thickness 10 micron more or 20 micron more or 30 micron more, means overall thickness is the 60, 70, 80, that this red curve shows that the thin crystalline silicon from 50 to 80 micron, bending radius is significantly increased, almost linearly. So 80 micron crystalline silicon substrate shows that almost 16 or 17 millimeter bending radius. However, microwire formed on the 50 micron crystalline silicon substrate, if we increase the length of the microwire to 10 micron, 20 micron, and 30 micron, overall bending radius is almost same. It's flexible. That means flexibility is maintained, although we increase the length of the microwires. Why? It is possible. When you do the very simple the simulation, during the bending process, the mechanical stress only applied on the bottom substrate, not in the microwire array. Because it is due to the spacing between two different wires, all the mechanical stress can be released very easily due to this enough space between wires. So we can conclude that a microwire structure is good materials, a good platform to increase the surface absorption, means decrease the surface reflection while maintaining a good flexible property. So we fabricate the microwire, one-dimensional microwire on the 50 micron thickness bottom substrate. So in that case, diameter is chosen to be 2 micron, and the length is 10 micron and 20 micron and 30 micron. So as we increase the length of the microwire, overall absorption is significantly increased. But interestingly, from 20 micron to 30 micron, there is no big difference as a point of the absorption. And also the integrated photon flux, with 30 micron length of microwire, only 89% of the integrated photon flux. That means even with the 30 micron length of the microwire, 11% of the photon is gone somewhere. So we have to fix this issue to increase the total current as much as possible. This kind of tendency also can be seen in the solar cell device. When we fabricate the crystalline silicon flexible solar cell with microwires, until 20 micron microwire length, the overall efficiency was significantly increased from 10 to 15%. However, although we changed the length of the microwire from 20 to 30, the overall efficiency doesn't change much. It is very similar result as I explained in previous, that this is due to the overall current is saturated. And meantime, the voltage can be decreased as we increase the length of microwire. Makes sense because as we increase the length of microwire, total the surface area is increased. That means the surface recombination getting more important. So overall open circuit voltage can be decreased a little bit. But issue is that why this total current is saturated, although we increase the length of microwire from 20 to 30 micron. So we studied a lot to solve this issue. Finally, we found the key problem of our structure, because initially we applied the cylindrical shape of the one-dimensional microwire structure. Still, there are flat top surfaces, all the microwires. So we estimated simply of the total surface area of this flat top area is 24%. That means although we apply the although we apply the microwire array structure on the silicon surface, the 24% still is active reflection region. So to improve more the solar cell current density, we have to minimize this flat top surface area. So we employ that the tapered microwire. So if we make the tapered microwire instead of the cylindrical shape of the microwire, it shows better anti-reflective surface performance, because you know what, the diameter of the wire is getting gradually increased from top to bottom. That means effective index is getting gradually increased. So impedance mismatching between air and silicon is getting smaller and smaller and smaller. So how to make this? It is pretty simple. After fabricating this one-dimensional wire structure on silicon wafer, we just put into the isotropic silicon etchant, a so-called RSC100. It is the commercial product. So you can use any isotropic silicon etchant because you know what, the silicon etchant can easily access to the top wire part and then getting the less effectively approach to the bottom part because it is the sort of the porous type structures. So the top part is getting more etched and then bottom part less etched. So finally we can have this kind of very nice one-dimensional tapered structures. This line profile from bottom to the top also show that it's very nice profile. Show that it is perfect tapered structures. So finally, with these tapered microwire structures, we fabricated a flexible solar cell. The left image show that it's finally fabricated flexible solar cell, and with the polymer capping layer on top and bottom. It is pretty simple method. You can use any polymer layer onto the bottom and top, and then this microwire is very stable. Although we give a mechanical stress on top, the microwire can be stable without any break. So, and also we apply the localized back contact, which is the very common technology used in the industry. So finally, we have over the 18% overall efficiency of the flexible solar cell. This is the is a very meaningful, and then at that time it was the best efficiency flexible in 2018. So was is a sort of the important value in the flexible solar cell application. And meantime, we also did the bending test, 1,000-time bending test with this kind of experimental setup. So through the 1,000-time bending test, the overall efficiency was very stable. And then field factor and short circuit current density and open circuit voltage, all of the photovoltaic parameters were very stable. So it means that this device is very stable during repeated bending test. Also, as a demonstration, we fabricated a simple 4-unit cell-based flexible module on image on the right side. And then we apply this flexible module on the simple electronic watch strap. And based on this, using this solar module, the electronic watch can be supplied the electrical power. So in this video, without the light, watch doesn't work, and with light, watch shows the time. Okay. So far I explained that why we have to use the one-dimensional microwire for flexible silicon solar cell application. The next topic is that what's the optimal geometry of these one-dimensional wire array structures? As I explained before, the diameter is almost fixed because by considering the practical device fabrication, we have to choose the 2-micron diameter of the wires. Only remaining parameters is the spacing and length. So by changing the length and spacing, we studied the theoretical maximum current density we can obtain through the FDTD simulation. And finally, we have this kind of short circuit current density map. And by changing the spacing and the length of the wires, we can find out the theoretical maximum value of the short circuit current density. So although this map is very simple, but we can find very important things. We can learn very important things from this map. So most important thing is that the spacing is the most dominant factor that determines the theoretical maximum short circuit current density. For example, 200 nanometer diameters, regardless of the wire length, always we can try to obtain the maximum current, almost maximum current density. So around the 43 value. So based on this map, we try to find out the 200 nanometer spacing of wires and the almost 10 micron length. It should be show that the about the 43 milliampere per square centimeter current density, which is very meaningful value. So we fabricate the structures, 2 micron spacing and 1 micron spacing and 200 micron spacing with the 10 micron length of the wire with the 200 nanometer, 2 micron diameter of the wires. And we compare the absorption spectra with this different spacing. Based on this result, the experimental value almost similar to the FTD simulation result, and also that experimentally estimated maximum current density value is very close to the theoretical maximum current density of 43 in case of 200 nanometer spacing. We also fabricate the device with the 200 nanometer spacing, and also we observe the over 42 milliampere per square centimeter. It is very high value, and it is very close to the theoretical maximum current density. So if we control the spacing, for example, with the 200 nanometer spacing, we can fabricate the almost highest current density solar cell can be realized. And next thing is the little bit different topic. So far I explained that it's a direct fabrication of the one-dimensional wire structure on the silicon substrate, but sometimes we cannot directly form the structure on the silicon substrate. So with the flat substrate, without any silicon surface structures, we can fabricate device. In that case, because we can decrease the surface, we can decrease the thickness of the silicon substrate as thin as possible. So we can realize more flexible device. For example, its bending radius is 5 millimeter. So in that case, we can wrap this silicon wafer on the surface of the pencil, and this is the solar cell itself. However, still, the surface reflection is the issue of this solar cell. So in this case, we can apply the structured polymer sticker onto the silicon surface. We use the PDMS, and then we treated surface structure with the random pyramidal structure on the PDMS, and then prepare it as a sticker and then we apply this sticker onto the silicon solar cell like this. And then this shows that the convex bending and concave bending and very stable and very stable photovoltaic efficiency result. So finally, we fabricate the device, conventional homojunction solar cell and then heterojunction solar cell with almost 20 micron thickness crystalline silicon bottom crystalline silicon wafer, and then fabricating solar cell, and then we apply the pyramidal structure pattern, the PDMS film onto the solar cell. And then it shows the over 18% efficiency, very similar to the direct fabrication of the microwire onto the crystalline silicon. But this structure, this device is more flexible, and then because this film can be easily replaced repeatedly. So as a practical application, this kind of approach is also very meaningful. I'm sorry, why slide is back and forth. And also that we did the bending test is a routine process. It shows that very stable efficiency and field factor and short-circuit current density and open circuit voltage during the 1,000 times bending test. And also the surface structure can show better angle incidence compared to the the flat surface, and also that the because sun is moving by change the time and by change the season, so the angle instance is very important. So with this PDMS structured film on the silicon solar cell, better angle instance, and it is very meaningful even for the practical application. So this is the last slide. You know what, the PDMS I used as a sticker for the flat surface-based solar cell is also known as very good radiative cooling materials. So only apply this PDMS film on the top of the surface, we can decrease the overall device temperature during the daytime. So in this test, we only simply do the 30-minute experiment, once on condition. Without the film, surface of the crystalline silicon temperature increased up to 55 degrees Celsius, over the 55, the yellow color. However, with PDMS structures, it is still 35 degrees. So only 30-minute difference, 30-minute test, 20-degree difference can be observed. Why it is important? You know what? Solar cell, the temperature is very important. As increase the device temperature, overall efficiency of device is getting decreased. So we have to maintain the temperature as close to the room temperature. So this kind of thermal management is very, very important in the solar cell application. So this result is sort of the a very preliminary, although it is very preliminary, but PDMS kind of the radiative cooling materials very simply cool down the device temperature during the operation under the sunlight. And also meantime, it can control the surface reflection, and flexible application is also the available. So I think that this is the one of the topic we have to explore more in this related research. Okay, these are all I prepared today. So I would like to thank for the funding agency and all of my group members. And okay, I am happy to get any question. Thank you.
Hi, Professor. See you. Thank you very much for your great talk.